We know the limit as x approaches 3 of 2x minus 1 equals 5. The question is, for what values of x guarantee that f of x equals 2x minus 1 is within first 1 unit of 5, then 0.2 units of 5, and then finally epsilon units of 5. This problem introduces the formal definition of a limit. Before we review this though, if we want to know for what x values f of x is within 1 unit of 5, we can set this up as a compound inequality. We want to know when the quantity 2x minus 1 would be less than 5 plus 1 and greater than 5 minus 1. So if we solve this compound inequality for x, we can determine for which x values f of x is within 1 unit of 5. So let's first simplify. 5 minus 1 is equal to 4. And of course 5 plus 1 is equal to 6. Now we'll begin to isolate x by adding 1. So we have 5 less than 2x less than 7. And now we'll divide everything by 2. So we have x is greater than 5 halves and less than 7 halves. We're converting to decimals. X is greater than 2.5 and less than 3.5. So these are the values of x that would guarantee f of x is within 1 unit of 5. Before we look at this graphically though, let's look at the formal definition of a limit. The limit as x approaches a of f of x equals L. For every given epsilon greater than 0, there is a number delta greater than 0, so that if x is within delta units of a, where a is the value we're approaching, and x doesn't equal a, then f of x is within epsilon units of L. So because we're trying to find the x values that were within 1 unit of 5, for part A, epsilon would be equal to 1. And because we're approaching 3, notice how these x values are within 0.5 units of 3, and therefore for our definition, delta would be equal to 0.5 or 1/2. Looking at this graphically, remember the limit value is equal to 5, so we wanted the function value to be within 1 unit of 5, so 5 plus 1 gave us 6, 5 minus 1 gave us 4, where epsilon was equal to 1. We found the x values that guarantee the function values within this interval were from 2.5 to 3.5, or 3 minus 0.5 to 3 plus 0.5, where this interval was a minus delta to a plus delta. Now for part B, the question is similar, but now we want the function values to be within 0.2 units of 5. So we want to know for which x values the quantity 2x minus 1 would be less than 5 plus 0.2, and when 2x minus 1 would be greater than 5 minus 0.2. So simplifying, we have 4.8 less than 2x minus 1 less than 5.2. Next step again, we add 1. Simplifying, we have 5.8 less than 2x less than 6.2, and now we divide everything by 2. Now simplifying, notice how we have x would be greater than 5.8 divided by 2, that's 2.9, and x is less than 6.2 divided by 2 is 3.1. So these are the x values that guarantee f of x is within 0.2 units of 5. Part B, epsilon was given as 0.2 based upon our limit definition. And notice how here these x values are within 0.1 units of 3, the value we're approaching. And therefore, when epsilon is equal to 0.2, delta is equal to 0.1. Now I should mention delta could be smaller than this. If this interval was smaller around x equals 3, it would still guarantee that the function values would be within 0.2 units of 5, but this would be the maximum value of delta that would satisfy our definition. Now for part C, we're going to generalize. we want to determine for which x values guarantee f of x is within epsilon units of 5. So again, we'll set this up as a compound inequality. We want to know when the quantity 2x minus 1 is less than 5 plus epsilon and greater than 5 minus epsilon. So we'll begin to isolate x. So our first step will be to add 1. So we'd have 6 minus epsilon less than 2x less than 6 plus epsilon. And then we'll divide everything by 2. And we'll show some extra work here. We'd have x greater than, this would be 6 divided by 2 minus epsilon divided by 2. X is also less than 6 divided by 2 plus epsilon divided by 2. So finally simplifying, x would have to be greater than 3 minus epsilon divided by 2 and less than 3 plus epsilon divided by 2. So these are the x values that guarantee our function value f of x is within epsilon units of 5. And part C has a lot more power than parts A and B. To generalize, if we want the function values to be within any epsilon units of 5, notice the x values must be within epsilon divided by 2 units from 3, and therefore delta would be equal to epsilon divided by 2. As long as delta is equal to epsilon divided by 2, the x values will always guarantee the function value is within epsilon units of 5. This result has a lot more power because now, if we're given any value for epsilon, we can determine delta to satisfy our limit definition. I hope you found this helpful.